G'day everyone, how's it going? We're at Spectro Scientific today, and I thought it'd be worth going through some of their field analysis kits. So if you remember when we talked about oil analysis in the past, there's a couple of different levels of oil analysis, so to speak. So you've got your sensors, which happen to be real-time monitoring. So that's probably layer number one. Layer number two is the field style oil analysis. So these are kits that you can either take into the field. So this would be an example of one that you would potentially have actually next to a piece of equipment versus something like this, which you would set up as a lab on site, right? So that's kind of level number two. Level number three is where you go into what you might term the traditional oil analysis, which is us taking samples and then sending them off to the lab. And then level four is probably that next level down, which is what you might term exception testing. So still done in a third-party lab, but we're doing more investigative type of work, right? So that's where this all kind of fits in. Now, to me, we kind of need to be viewing oil analysis in a similar way to what we do with some of the other condition monitoring disciplines. So as an example, everyone is very comfortable with the idea that with vibration analysis, we have a number of different levels. So if I have a very expensive gas turbine, I'll have a vibration sensor that's on the turbine, and that's picking up bearing faults. Now that's happening in real time and collecting data on a second-by-second basis. And that makes sense because the value of that turbine is so high, we want to be able to detect any kind of fault instantaneously and potentially shut the turbine down. The next level down, we might have, there's a little unit that SKF sells. I've actually got one at home. I'll probably insert it here. So SKF sells a little one, which is basically traffic light analysis. We stick it on a motor, and then we see, is it green, yellow, or red? That's giving you very indicative vibration analysis. And then another level down is where we take vibration analysis, we're going to do our polar plots, we're going to do our frequency analysis, and we're going to diagnose exactly what is happening inside the machine. So we're all very comfortable talking about that when it comes to vibration analysis, but with oil analysis, people are still stuck in this mode where it's, I take samples and I send them off to a third-party lab, and that's the only kind of analysis that there is. So what we need to do is we need to move to kind of a more mature and maybe more sophisticated view of oil analysis and see that there's kind of these four different types. They all have their place. All right, so let's start with probably the FieldLab. All right, so this is the FieldLab 58. There's a couple of different versions of the FieldLab. So one of them is the 33, this is the 58. So the 33 is going to do basically infrared, as well as viscosity, as well as ferrous density. This one's slightly different. We're going to do viscosity, as well as infrared, as well as a particle count, as well as a kind of elemental analysis, which is a little different to what you'd see on like an ICP or an OES. We'll get into that in a second. Now, the process for this is actually pretty simple. So, got to take one of these. All right, so we're going to test some Valvoline engine oil. I haven't chosen this for any particular reason, right? But what we're going to do is just use this pipette. Okay, draw out a sample. Here you go. Now you might want to wipe it a little bit on here just to make sure that there's no excess. Okay, first thing, right, we're going to set up this unit. And so we're going to go to, hopefully you can see that, it's measure fluid. Okay, first the sample. Yeah, we'll pick up a sample ID. It's kind of like a here's one I prepared earlier type deal. Once we've done this, now we don't have to do this necessarily in order, but we are probably going to zero the filtergram just to get it ready. Now, the filtergrams. What this is effectively like is kind of like patch analysis, but it is calibrated to a certain size of patch just so that we can get a couple of measurements out of it. So, fortunately, this machine will do kind of like instructions. So you can press play and it was going to give you some instructions on how to do it. So here, I open this, place this in. I close this, right? And then we press 0. Okay, so that's going to go on in the background while we're doing some of the other tests. So now that we've kind of stepped through, the idea is go to viscosity, right? Now it says the viscometer is already ready, so we can press start and insert the sample. Hang on. start. Okay, going to insert the sample here. Oops, do I just put that here and hold it?
Press the valve on top. And when it's done, pull it out and then release.
All right, so while the viscosity is measuring, we can go to chemistry. So when they say chemistry, this is actually the infrared side of the analysis. All right, first thing, a new background is required. Please make sure that the cell is out. So that's this thing here, right? And we're going to press start just to do a background check. Right, so we can run some of these tests sort of simultaneously. So you can see the viscosity is still testing while the chemistry background check is done. Yeah. Okay, so we're going to skip around a little bit here. We can go back to the viscosity, test completed, and it'll give you the viscosity at 40 degrees C, so 87.8. Obviously, if we're testing engine oils, most of the time we're usually trying to measure at 100 C. Obviously, in an industrial setting, 40 C is what we're doing for most of the ISO viscosity grades. You could, for example, calculate out a viscosity at 100 C if you know the 40 C as well as the viscosity index, right? Assuming that there's been no shearing down of the oil. So that's us testing the viscosity. So that was all done just in this very, very small cell. Okay, in the meantime, chemistry looks like it's completed the background check. So as a result, right, there was no fluid in there. So we can open up the cell. Okay, I'm going to take this little pipette again. Do the same thing and put a little drop on here and then close up the cell again. So put this in and then press start. All right, that's all kind of completing. And again, in the meantime, we can go on to the next level of the analysis. So can we go back into the 0 filtergram just to check that it's complete, or?
It'll tell you when you go to particles. If it wasn't completed, it would tell you.
Oh, okay. All right, so next step is to go into particles. Right? So take filtergram from elements, place it in the particles, insert syringe with sample. So the syringes in this case, right, is something like this. So the way that this is going to work, and you'll see it in action, is that we have an entire syringe, and this is actually going to give us two separate measurements. So in here, right, we are going to be forcing the oil through this kind of filter. So this is doing particle count by what we call the pore blockage method. Now, this is one of those ones that's taught in MLA, but very rarely seen, right? So pore blockage method basically relies on us pushing a syringe of oil through this filter patch, which is a 4 micron membrane. And then what it's going to do is kind of look at the, let's say the pressure buildup, right, as this syringe forces the oil through it. And based on that, we can get a calculation of the 4, 6, and 14 particle counts. Now, once that's done, we're going to be able to put it into the XRF, and we're going to be able to get elemental analysis of any of the wear debris that is on the patch. So, all right, so I'm just drawing this in here, right?
You're going to put the filtergram in there.
Oh, isn't there one in there for the 0?
That's the one you want to take out and move to the
Oh, yeah.
particle count.
I forgot the steps here. All right, so remember that we had our 0 membrane in here. So we're going to pull this one out. Okay, this is going to go, do I need to lift this up? Yes. Push this one in here. Okay, close that up. So that's the filter patch. And remember, if you ever forget the steps, which I have a couple of times here, you can always hit play, right, and it will give you those steps. Now, we're going to say we've already shaken up the bottle, pull out a sample, and we'll say approximately to 12 mil. Oops, wrong one. All right, so here we go. Into the hole, push that in. Okay. All right, and then we just press start. So. Now this is a pretty clean oil sample, so we're expecting that probably most of the volume is going to go all the way through. If you had a highly contaminated sample, it might already register the pressure differential when we've maybe only used up half the sample or something like that. But as that's measuring, it's going to give us the particle counts, and then we'll be able to take the filter and then put it in the XRF machine. Now while that's going, the infrared has already done, so we could actually go back here under chemistry, and it's going to give us total acid number, oxidation, and as well as water. So most of the kind of like a little bit of contamination as well as degradation is going to be covered by the infrared. In the meantime, particles is almost 70% done. All right, so now this is telling us we can remove the syringe, all right, because that's all done. So I'll place that over there. Hit the continue button. It's just going to close that. And it does a drying cycle. All right, so now that's given us a particle count here. So in this case, the particle count is a 20, 18, 15. Obviously, if you had an oil that was in use, it'll probably show up dirtier. This is relatively clean oil, although terrible me for sample hygiene. I should always be closing bottles. And it will actually give you the particle counts as well. So it'll give you the number of particles that was counted in the 4, the 6, and the 14 ranges. All right, so once that's done, you can press continue, okay, and it will release the little filter here. So we can pull this out. Obviously, because it's gone through the drying cycle, it's not sort of like covered in oil. And the next step is elements, right? Which again, so we're just stepping through the process. Now, ensure the bottom of the filtergram is clean, which it already is because of the drying, but we'll just wipe it off a little bit here. Insert it into the module, right, which is back in the same place that we did the zeroing earlier. Okay, and then I close it, then press start. All right, and now we wait. All right, and now our test is complete, and we have all the elements that an XRF can measure, which is basically anything from magnesium down. That's sort of like the restriction on XRF is that they can't really do kind of like lithium and the lighter elements. But that's fine because for the purposes of wear metals, that pretty much gives us everything we need. So we've got aluminium, silver, cobalt, chromium, etc., all the way through to zinc. And now what this is really, really useful for is, number one, we can take out this little unit. And because we have a prepared filter patch, we can actually do some, for example, analysis through a microscope, right? In a similar way to what you'd do a filtergram or a ferrogram. So it gives us that capability. Because these are very repeatable, it's also calibrated for the XRF, and we are getting these elemental results. Now, a couple of things to keep in mind, and where I think this is a pretty handy unit. Let's say, for example, I have like a gas turbine, and I have wear that's occurring. A lot of the inline sensors will identify that wear is occurring, and that's hugely valuable information. But what I want to do is that I want to take that information and say, well, which part of the turbine is wearing out? And this is where the XRF analysis comes in useful, because the wear particles will be deposited on this, right? And then we can get an idea of, is it the white metal bearing, for example, right? That'll show up in a specific elemental signature. So I think this is extremely useful in a number of different applications where you want to identify the specific kind of wear metal. Now keep in mind, this is not elemental analysis the way we do it in ICP, where we're identifying soluble things like additives and other soluble contaminants. So let's say, for example, if I were in an engine oil application and I see copper in this result, I can be confident that it's actual bearing wear as opposed to leaching of the copper coolers, right, which would be actually a soluble form. Because if it's soluble, it won't be captured by the filter patch. So this is the FieldLab 58. Super useful super useful for certain applications. And I think gas and steam turbines, so anywhere where you've got tilting pad bearings, engine analysis as well, where you're trying to identify, are the wear metals aluminium, are they iron, are they copper, tin, all of that sort of stuff. FieldLab 58, super useful. Now, this is XRF, So what's the limitations? Like when would you use XRF versus a standard ICP type oil analysis, whether it's rotating disc electrode or OES? Now, I think that each of these different technologies kind of has a bit of a place. Now, XRF, for example, is going to be maybe a little bit less sensitive to particle size, where your standard ICP, we usually say kind of tops out at, let's say, an average of about 10 microns in size. So that's one of the strengths of XRF. As I explained earlier, you are a little bit limited in that you can only kind of test from on the periodic table for about magnesium down. So that ignores, the light elements would be boron and lithium and sodium are probably the only ones of interest in oil analysis that can't be picked up by an XRF. So a relatively small limitation. And when it comes to wear metals, almost completely irrelevant, right? So there is nothing in the wear metals that I can think of that is made from boron, sodium, or lithium, right? So in that respect, when we're testing wear metals, there's really kind of no downsides to using XRF. All right, so now we're in kind of what is the MiniLab setup. That's an interesting kind of naming convention because the MiniLab is mini relative to a usual lab, but it is larger than the FieldLab. So when we're talking mini, it's relative to like a third-party lab, right? But this is the difference between this and the field labs is this has got a little bit more modular, right? So where the field labs are kind of like in a Pelican case and it's all mil-spec rated, you can take it into the field, dust and contamination is not as much of an issue, you drop it, yeah, it's not ideal, but it will probably survive. This kind of stuff is more made for benchtop type activity, but it is still portable. So as an example, right, this is the FluidScan, which is in the field lab. But if you disconnect this, you can actually take measurements out in the field with you. Hence, well, it's got these handy holders. Exactly the same thing here. So this is the MiniVis. So this is the viscometer that was inside of the field lab. Again, you can remove this and take it with you if you really want. When it all sits on this bed, it is part of the MiniLab and all the data is kind of integrated. At the back here, we have a particle counter which operates on LaserNet Fines. So most people have kind of heard of LaserNet Fines, may not have actually seen the unit itself. So typical optical particle counts, right? We are sending a stream of oil and we have a light that's shining through it and there is a detector on the backside and it's seeing shadows. With LaserNet Fines, we actually have kind of an optical camera inside and it is taking images of the flow stream as it goes through. Based on the shape and the size, we can get particle count, but we can also do things like identify water, for example, and remove that from the particle count. So that's the advantage of LaserNet Fines. On top of that, it can also give you characterization of some of the actual particles themselves, right, based on the shape and the morphology. So now we're going to do the actual LaserNet Fines. So we go into the computer, press play on the particle analysis. Again, this is going to tell us what to do. Insert the sipper tube and click continue. All right. So this is the sample that we want to, like, this is one we prepared earlier. Yeah. Oops. I'm not good at this stuff. All right. Click continue. All right. And now it's going to process the sample. That's going to take a little while. So in the meantime, we might look at the elemental analysis by rotating disc electrode. This is the big boy, right? And this is also the one that's the most fun because it like makes sounds and does stuff. So Spectre Oil. There's a couple of different versions of this and it's basically just testing different elements, like the calibration that's set up on the inside is a little bit different. This is kind of the guts of everything. A couple of things to note. You have one of these and I can get one out, one of these. Okay. A couple of things. These need to be sharpened right before that they're placed in the holder, and these are a consumable. So, right, this is a one-time use. If you want to have a little look at it, there you go. Hopefully it focuses. All right, so these are a one-time use and are discarded after the test. So what you want to be doing just put that here for the moment, is, okay, we've got everything set up except for the actual oil sample itself. Again, here's one we prepared earlier, right? That's going to go into the holder. And I just push this, whoops. Sorry, and then I just pull this lever. Okay, so that's now submerged it in the oil sample, right? I think that's all good. Close the door. All right, and then we press start, and this is where like the fun stuff actually happens. I'll bring it a little bit closer. All right, so that's the exciting bit. Sparks fly, all the rest of it. Now, what's going on in the inside here is obviously we are exciting the sample and we are trying to give it, in basic terms, we're giving it a whole bunch of energy, and it is then going to disperse that energy. And then we use the wavelengths of light which get emitted from the sample to then measure the elemental composition of the sample, right? So that's RDE. Now, the reason why it's called rotating disc electrode is because this is the rotating disc electrode, right? Makes sense, right? Most of the stuff in, if you haven't figured it out, most things in our industry are not very creatively named. They usually do what they say, just like this channel, Lubrication Explained. So that's rotating disc electrode. It's slightly different from the typical ICP that you would see in a third-party lab, purely by the method of excitation, right? So in this instance, we are using the rotating disc electrode. In other methods, what we are doing plasma, and this one is arc, right? So slightly different method, but more or less the same principle. All right, so now our sample for LaserNet Fines is done. And per the instructions, I've got to start the flushing cycle. It makes sense, right? We need to clean the thing out. So I've used this, and I haven't done that very well because the easier way is actually just to raise this. Okay, we're putting the sipper tube down. And then continue. All right, so our LaserNet Fines analysis is done. I'll have to bring this a little bit closer. Right, so you can see on the computer here. Can you see on the, yeah, you can see on the computer, right, we've been able to identify based on the size and the shape, fatigue, cutting wear, sliding wear, non-metallics. I think that's based on the reflectance. You've got water bubbles as well as fibers. All right, so that's LaserNet Fines. So again, kind of a useful diagnostic tool, right? Not only to be able to see the actual level of contamination and the ISO code, but also the different kind of like wear morphologies. So I think that's really handy. All right, so that was everything. This is not the full range of Spectro Scientific products. It is most of them, right? And hopefully you've got an idea for FieldLab versus MiniLab. So very much something that can be taken out like around the equipment versus if you have an actual lab setup. So hopefully, just in doing this demonstration, what we've shown is these are pretty much idiot-proof, right? That was actually my first time ever running any of those analyses. I've seen it done once, but that was it, right? So I'm just kind of fumbling together, following instructions. Now, if you've got people that are in the field that are actually doing this testing on a daily basis, multiple times a day, they're going to get extremely efficient at doing these tests, and you'll get much quicker and much more efficient than I was. The kind of insights that you can get from field analysis, I think, are really, really useful. And again, going back to that sort of seriatim of different types of testing, where we've got online actual sensors, then we have the field type analysis. Then you'd probably argue actually that these units over here kind of sit below that, which is a field lab, not the field lab, but a lab that you have set up on site, right? Then underneath that sits third-party lab analysis, and then below that is your exception testing that you might do at a specialized lab. So again, we got to sort of construct that sort of pyramid and decide which analysis is appropriate for which application. And I fully expect that over the next couple of years, what we'll kind of move into is this mode where most sites are using a combination of all of those 5. That's really kind of where I'd like to see industry get to. So yeah, thanks to Spectro Scientific for hosting me and letting me play around with all of their equipment. And yeah, see you next time.